Okay, our final talk for this session is from Alexander,
Yep.
Sasha,
Yep.
Plavin, and he will talk about DictArrays. Over to you. Thank you.
Yeah. Hey, thanks everyone. Indeed, I will be talking about DictArrays. I titled it like efficient type unstable collections, and I will explain what it is and how it's possible. So first of all, kind of for the context in general. So in Julia, you have the ability to use these lightweight tables, basically without going for involve like some fancy custom data structures like DataFrames or stuff. You can just use vectors or abstract vectors of named tuples as tables, and you can choose. Depending on the abstract array type, you can choose row-based, column-based, everything like this. And there are a lot of functions, including functions in base like map filter, that can just make it convenient and straightforward to work with these lightweight tables. It works great for a wide variety of use cases. However, given that to be performant, these tables like named tuples and everything, they should be kind of known in compile time and compiled for every kind of set of types in the named tuple. These kind of type stable collections, they really struggle with huge number of columns. By huge, I mean like starting around either many hundreds or 1,000 and going upwards. So here I show just an example of struct array. First of all, if you just create a struct array with a few columns, like here in this example too, but it works fine all the way to like 100 or several hundreds, there is very little compilation time. It just not really noticeable in actual usage. However, if you want a table with how many 10,000 columns here, even just creating a struct array, it already takes 9 seconds when I benchmarked it. And of course, any downstream operation, be like even simple filter, it will also take a long time because Julia will compile all the functions for these huge tuples with thousands of objects. So I mean, you don't often need very wide tables, but sometimes you do. And what are the solutions if you really don't want to pay the compilation penalty? I mean, you can just ditch the collection interface and use some custom types like DataFrames, memory datasets. Um, Alternatively, if you like the collection interface as I do, you can use type unstable collections. Maybe you can just put dicts or dictionaries into your vectors and say, okay, now these are my table rows. It does work. Everything works in this scenario. However, operations are slow as soon as you get heterogeneous types in your columns. So the package I'm presenting here, DictArrays, it kind of gives you best of both worlds. It gets fast compilation from the kind of similar to type unstable collections, but it gives you fast runtime for like all the supported functions, same as type stable collections. So just show it like kind of fast compilation. I mean, like yeah, here it is 1,000 columns in the top, so the compilation is almost instant. It really doesn't specialize to all the set of columns and all the names and types. And StructArrays struggle with even with 1,000 columns. I think actually this was benchmarked on a different machine, so these timings are not compatible with what I shown on the previous slide. But I mean, it takes a lot of seconds for StructArrays or Vector-of-NamedTuples to compile with 1,000 columns. Um, for DictArrays, below I even show example with 10,000 columns. I wonder if anyone has a use case for that. But of course, the compilation time doesn't explode. It still stays like comfortably below what is noticeable. It also gets you fast runtime. So here I create also some DictArray. It can be a few columns. It can be thousands of columns. But if you want to map, filter, apply some of these functions, it works at about the same time, like almost exactly the same time as type stable collections. So here I show that the timings are almost the same for DictArray and for StructArray, but for StructArray you pay a lot more for compilation. And in the bottom there is a baseline how much time the same map would take if you just had a vector of dictionaries. Of course, it takes much longer because you need the dynamic dispatch for each row. So this is what you get with the DictArray, then kind of to how it works. Of course, it's not without tricks. First of all, the structure itself is very simple. It just contains a dictionary of columns, so it's column-based storage. Similar, basically, think of it as StructArrays, but based on dictionaries, not on named tuples. And some functions like getting an index. It is also done in a straightforward manner. You just get create a dictionary with the proper element from each column. The tricks come in the map implementation, and this is almost the only case, almost the only place where they come. So really, kind of for an generic, like for an arbitrary lambda function, if you pass an arbitrary function to it, there are some tricks to understand what properties the function needs, so that not to pass it like a huge name tuple with thousand fields. So it goes in kind of like this iterative way, passes an empty name tuple to function, checks what property try to access, adds the property to the name tuple, and goes on until the function executes correctly. And this is really kind of a hack or a trick, but it works fast. It works fast because kind of this addition, like adding properties to the name tuple, it only happens once for every property accessed by the target function, not once per row. So if your function accesses like 2-3 properties, it will be instant, as we saw in the benchmark here. There is also a less hacky but still fast path for if you pass not an like opaque lambda function but an object from Vectors-of-NamedTuples, because they are natively inspectable, so you can just inspect the function and see what property, inspect the object and see what properties it accesses. So this is kind of we explored both the outcomes that you get and the idea of the implementation. Now to the summary. So DictArrays, as I said, it's like StructArrays, but built on dictionaries instead of named tuples as a storage, with some tricks to make it fast. It is kind of living proof that both parts are possible. Native performance of type stable collections with all the like higher order functions that Julia uses, and also at the same time low compile overhead, even with thousands of columns with different types. And it supports both the collection interface, like array-like interface, and tables.jl, so it can be read or written to any table data format. So this is a nice experiment. I thought I will be using it more, but when really kind of looking at my personal use cases, I found that I never really go above like 100 or 200 of columns, and this is already happens very readily. And especially in the recent Julia versions, I noticed that compiler is really good enough up to like several hundreds of columns with StructArrays or just named tuples. So I just kind of treat this now as an experiment. It works. I just don't personally have a use case for that, but it should still be useful if you like collection interface and want to work with tables with thousands columns. Yeah, let me know if you're interested in that. That's it from my side, and looking forward.
Thank you.
For
I think we have time for one question, maybe, while Mark sets up. Is there a question? I have one actually,
yeah.
which is what do you think are the downsides of using this package against, either native arrays or struct arrays?
What is the first one?
Either native Julia arrays or struct
Oh,
arrays.
yeah. So the downside is that it shouldn't realistically be an abstract array, because there are so many functions that fall back to kind of iteration over abstract array elements, and this will be slow. So it doesn't have like 100% compatibility with functions that take abstract arrays. That's, I guess, the main downside. So you need to be careful when working with it.
Thank you. There's a question from Anshul. Quick one.
Do you implement the tables.jl interface with this? Do you implement the tables.jl interface with DictArrays? Oh, sweet.
Okay. Thank you. Thank you, Sasha. A round of applause for Sasha, please.
Stable.
We have a minute before we.
Correctly pronounce it. Yeah. That's the easy part.